So we're in the destructive test processing area. This is outside of the EPA because we're destroying the parts anywhere. Back in this area, this is our corrosive chemical handling. So this is decapsulation where we're using acid. And they're not the general use acid. These are the nasty acids. Plus HCT, or heated chemical testing, are done in the corrosive areas. And I don't actually have access to even get in those rooms because I'm not a trained chemical handler. That's what we do in those areas. So we're doing, like, for example, decapsulation. Because that stuff is still corrosive, even the residues from it is done in a fume hood. And then this is where we do solderability testing and cross-sectioning, so very destructive processes. Cross-section is where we actually cut a device. It doesn't have to be in half, but we cut it across so we can see the inside profile of the device. On MLCCs, we can see how many electrode layers they are. So the golden sample has 50 electrode layers. So we want to make sure that the new sample actually has the same number of electrode layers. Or we can see where there's delamination, where layers are starting to separate on devices. Cross-section we also use for failure analysis, but we also do the decapsulation, the wafer analysis. So the system that we're using, the microscope that we use for this goes up to 5,000 times magnification. Micron, for example, has tiny, tiny, tiny dye markings, which a scope even up to 1,000 times magnification cannot identify, or I can't get a high.
So right now, as he's doing right now, he's magnified. Is he what range? Is he magnified 5,000 times, or how?
Derek, what magnification level are you at?
Come on, take a look at this a little bit.
But the decapsulation process itself is just exposing the dye. So when you say decap, all we're doing is we're removing the insulation around the device to expose the dye itself. But it's the analysis on the dye, which is really the part of decap that everybody's interested in. Here we're on dye analysis. We are looking at the architecture, how the circuitry is laid out. We're looking for traceable dye markings, anything from the manufacturer's logo to a part number. It could be an internal part number.
Does the factories give you markings, or are there sheets that they can say we compare to that say this is the original item? Or
TI used to. Okay. TI used to have an image of their of the dye topography. I think they realized people were using it to copy the parts, so they stopped doing it. So no one publishes this.
So the best way is to have actually a golden sample and then to match it with an
if we don't have one already on file.
Okay.
We do have thousands of part numbers on file, but there's billions of part numbers out there, so you're still looking at a snowball's chance of hell of finding the one that you're looking for. So a golden sample certainly is the best way. Golden sample needs to come with traceability. We need to receive it with the traceability so we know it's really a golden sample. Somebody just giving us a part and saying, here's a golden sample.
Yeah. Is it off the shelf?
I have no idea where it came from, so we call
origination.
It. Correct. Anything that we've got on file that we tested before, we will refer to as a reference sample as long as the test was positive.
Okay.
But go ahead and go back, Derek. Right now you can see where we've actually got the the linear tech. We've got an LTC dye marking.
Okay, I can see right there. Okay.
Yep. So we've got traceable dye markings here to the manufacturer. We don't have a complete part number on that, but we do know it's an LTC part. Or sorry, linear tech. But also under decapsulation, we are looking for dye damage. So we can see ESD damage or electrical overstress. That part that we just saw that was shorted out. That was visible on the outside. But sometimes that damage has not materialized on the outside yet, but we can see it internally.
That's another service you provide.
Yeah, that's more in the failure
analysis. That customers come to you with a circuit or a component that had something happen, went bad on a board or circuit.
Correct.
And you guys test the board to see exactly what's going on inside of it.
Correct. Failure analysis starts with the application itself. Like somebody goes, all right, my TV isn't working. So we have to break down the TV to see where that failure occurred, and then if we break it, it's a step-by-step process, kind of like peeling the layers off an onion. Right? It wasn't that, it wasn't this. Then we get to the board level diagnostic. We have to look at the PCB itself, and then if it's not the PCB, we need to look at the componentry itself. So we started looking at each component to find out where the failure occurred, and then we have to break down the individual device to see why it failed. The damage could be caused by the manufacturer, the original component manufacturer, by some kind of control process. It could also be caused by the application itself, bad application design, or it could be a fake part. It could be any of those things and probably a couple other ones. So failure analysis is finding out exactly what went wrong with it.
You've probably seen everything under the sun with the failure analysis side.
We've seen a lot. This guy's probably seen a lot more. He is an outstanding failure analysis engineer. Very creative, and I mean, he can tell by the shape of the crater if it's from an OCM or it's from an outside source. Excellent work, but part of that is giving the guy the right tools. Boy, so, and part of that's giving him the right tools. This microscope that he's using now is outstanding, not just for decapsulation, but in failure analysis, even on marking permanency tests. We can actually look at the topography of the molding compound to see if it's been sanded down, and we can measure the height. You've seen the height,
yes.
You can see in a topographical map when it's all red and blue and green, depending on how high it is. We can do that on the molding compound to see where it's nice and flat.
It's been sanded or scraped or things.
Yeah, we can see it under a normal microscope, but it doesn't really. It's not convincing in the photo because it still just looks black. So this one actually can show the topography, particularly matched with HCT. HCT tends to get a lot of false failures. So using this kind of magnification or microscopy with it can really show if there's actually a coating that was removed or if we just dissolved it.